Okay, so um, welcome back to automated program verification. So far, right? I mean, we kind of summarize what we have done. So we have looked at different techniques for automatically verifying programs, right? And in particular, we looked at deductive verification, right, with constraint solvers. We saw multiple techniques in that particular module, right? Namely strongest post condition, weakest precondition, and for logic. But one of the limitations there was that the verification is not fully automated because the programmer has to supply the loop invariant. So to overcome that limitation, we looked at abstract interpretation, which is nothing but static analysis of programs. And so we went through the entire theory of abstract interpretation, right? And abstract interpretation overcomes the limitation of deductive verification in the sense that it is fully automated. So once the programmer decides on a particular abstract domain, and we saw different abstract domains as well, then they can analyze their programs, right, using the abstract domain. And if an abstract interpretation is a sound procedure, right, provided the abstract domain satisfies certain properties, meaning that any verification result that you obtain using abstract interpretation is going to be correct, right. So but abstract interpretation also has certain limitations, right. So namely that if abstract interpretation fails, right, meaning that uh, if it says, right, that the program is not correct, right, meaning that again, right, so since in abstract interpretation you over approximate the set of program states, right, at every program location, right, and based on that over approximation you decide whether the program is safe or not, right. But because of the over approximation, right, you may introduce imprecision, right, meaning that even though the program is correct, the abstract interpreter may say that the program is not correct, right, because it over approximates the set of program states, right, leading to maybe some error state, right, which is actually not reachable, but the abstract interpretation computes that it is reachable, right. So if the abstract interpreter says that the program is not correct, right, the programmer has no idea whether the program is actually incorrect or whether this was the result of the over approximation, right, that was introduced by abstract interpretation, right. So abstract interpretation is a sound but not complete procedure, meaning that if the program is correct, it cannot determine, right, whether the program is actually correct. So in all cases it may not be able to determine that the program is actually correct, right. And in particular, right, I mean, if it says the program is incorrect, it doesn't give any more hint, right, or any more clue as to what is this bug, right, or what is this incorrectness. So in an ideal scenario, right, the verifier should either say that the program is correct, right, in which case it gives a proof, and if the program is incorrect, it should also give a bug, right, which is an actual execution of the program, which results in the error state, right, or which results in some post condition not being satisfied, right. So this is what we will now move towards, right, which is to essentially also, or to come up with a verification technique which not only verifies program but also finds bugs, right, or gives us output the bug if the program is incorrect, right. So model checking is another technique, right, in automated verification which can do both, right. So it can prove that the program is correct, but at the same time it can also give an actual bug, right, meaning an execution of the program which results a buggy execution of the program, right, if the program is incorrect. Okay. So we have kind of seen model checking earlier, when in module 1, right, when we discussed constraint solver. So we looked at this notion of bounded model checking there, but the general idea behind model checking is to exhaustively explore the state space of a program's execution, right? Meaning that in any execution, so given a program, right, in any execution of the program, what are all the possible states that are reachable at any program location, right? So you exhaustively explore all possible states. So this is the simple idea behind model checking. The advantage here is that so if the error state is not reachable, right, meaning that let's say you have some error state, right, meaning there is some valuation of the variables, right, which you designate as error, right. So this is the specification of the program, right, that is given by the programmer either using assertions, right, or using precondition and postcondition, right. So the error state is given by the programmer. Now since model checking explores the entire state space reached during the program's execution, if the error state is not reached, then that means that the program is actually safe, right, and model checking will output safe. But if the error state is actually reached, right, then the path to the error state can also be reconstructed, right, meaning that what is the exact sequence of program locations, right, what was the exact execution, the transitions that were taken by the program in order to reach the error state. So this is what we call as a counter example, right, or a bug in the program, right. So if the error state is reached, then model checking will output the counter example. Okay. So for sequential programs, right, model checking comes in many variants, and that's what we are going to only discuss, right. So model checking is widely used for concurrent program verification, right, but in this course we are only going to focus on sequential programs, right. So for sequential programs, model checking comes in different variants. So there are 4 different variants, right. So you have concrete, symbolic, bounded, and abstract model checking. So all these 4 variants are kind of similar to each other, right. So they follow the same structure. So let's go through all of them one by one, right. So we start with concrete model checking, right, and the idea behind concrete model checking is to explore the concrete program states, right, that are reachable at every program location, right. So here I have given the algorithm for concrete model checking, right. So let's look at what it takes as input, right. So it takes as input this gamma c, right. So this gamma c, as we know, this is the LTS, right, of the program. So here also we will assume that the program is specified in the form of a label transition system, right, where you have a set of locations, right, program locations and a start location, end location, and transitions among these locations, right, which are labeled by the program statements. Right. So that is the format in which the program is taken as input by the algorithm, and then you have this set P. This is the precondition, right. So this is the set of initial program states, right, or start program states at the start location of the program, right. So this is what concrete model checking takes as input. Another thing, right, which concrete model checking assumes, in fact any model checking assumes, is the presence of a special location, right, which we call as the error location in the program, right. So this is typically denoted using L underscore ERR, right. So L underscore ERR, this is a special location in the program which is called the error location, right. So the idea is that if the program execution reaches this error location, then the program is incorrect, right, or it has an error. But if the program execution, right, if any program execution does not reach the error location, then the program is safe, right. So this is one way of specifying, right, what is the specification of the program, right, the correctness of the program. So the error location, for example, could correspond to an assertion violation, right. So you may say that, okay, if some assertion is violated, then you will reach the error location, right. If you have a post condition based specification, right, so if you have some post condition q, right, then essentially you can sort of assert, right, q, and if this assertion fails, right, so if this assertion fails, meaning that if the program state does not satisfy q, then you will reach the error location. Okay. So this is what is assumed by concrete model checking, right, which is the presence of this special error location, right. So now the idea behind concrete model checking is to find out whether or not is there an execution of the program which will reach the error location, right. So what concrete model checking does is quite straightforward, right. So it essentially executes the program concretely in the forward direction, right, and considers all possible executions of the program simultaneously. So the way it does it is by maintaining this work list. So this work list is what is it? So it is a set of pairs, right. So a set of pairs where each pair is of this form, right. So each pair is of the form L and a state sigma, right. So L is some location in the program, and sigma is the concrete program state, right. So this is the valuation of the variables, right, of all program variables, right. So it maintains a set of such pairs, right. So the idea is that at the program location L, the state sigma is reachable, right, and now what you want to do is you want to propagate the state sigma to all the successors of the location L, right. So this is what is done in this while loop. Okay. So initialization, right, so it initializes, so concrete model checking algorithm initializes the work list with again a set of pairs, right, and these pairs are of the form L0 comma sigma, right, where L0 is the start location and sigma is any state in the set of preconditions, right. So what we are essentially saying is at the beginning of the program, right, so at the beginning at the location L0, right, I have a bunch of states which are reachable, and these are all the states which are in P, right. So if you have, so you take any state sigma which belongs to P, right, so L0 comma sigma is what is reachable at the beginning, right. So it also maintains this the second set, which is called the reach set. So reach is also another set of pairs, right, similar pairs. So pairs of program locations and sigma, and again the idea is that if any pair is present, right, so if L comma sigma is present in reach, that means that sigma is reachable at the location L. Okay. So let us see what the algorithm does. So the while loop, right, it continues until the work list is non-empty, so until there is something inside the work list, and in every iteration it will pick one pair from the work list. So it picks L comma sigma from the work list and it removes it, okay, from the work list, and then it checks whether this L comma sigma is already there in reach or not, right. So remember that this L comma sigma, right, so this is like you are just discovering, right, that the state sigma is reachable at the location L. So therefore you first check the reach set to find out whether you already know that the state sigma is reachable at the location L or not, right. So if it is already reachable at the location L, which means you had already discovered the state earlier, you don't go do anything. But if say L comma sigma is not in reach, right, then I am going to add it into reach, and then I am going to propagate this sigma to all the successors of L. Right. So if you take the location L, right, take every successor, right, of the location L, right. So you take some successor, let us say L prime, right. So if this edge, right, from L to L prime, if it is labeled by the program command C, then what I am going to do is I am essentially going to execute this program command C on the state sigma, right. So the way I am going to execute it is by using the strongest post condition, right. So I modify the work list by adding new pairs, right, of the form L prime comma sigma prime, where sigma prime is obtained by executing C on sigma, right. So I know that sigma is reachable at L, so I execute C on sigma. So I execute C on sigma using the strongest post condition, right, SP sigma comma C. So this SP sigma comma C will give the set of all states that are obtained after executing C on the state sigma. So I know since the imp is non-deterministic, right, there may be multiple such states, so that is why it is a set, right. And now at the program location L prime, all those L prime comma sigma prime are reachable, right. So they are all added into the work list, right. So in the future iterations, right, these pairs will be removed from the work list, added into reach, right, if they are not already there, and then they will be further propagated, right, to the successors and so on, right. So this while loop will continue until the work list is not fully exhausted, right. So until there is some member in the work list. So after the while loop exits, right, meaning that the work list is empty, you then find out, right, whether or not in the reach set, right, is there any pair whose program location, right, the first component of the pair is L error. So if L error is present, then that means that the program is unsafe, otherwise the program is safe. Okay. So this is concrete model checking, which is essentially just executing the program in the forward direction, maintaining the set of reachable program states, right. So this is what we mean by exhaustive state space exploration. Okay. Now remember I said that one of the advantages of model checking is if the error state is reachable, then you can also construct the counter example, right, which is the actual bug. So the way to do it is, so this is concrete model checking with counter example generation, right. So the way to do it is I have added a few things, right. So the only change I have made is I have added this parents thing, right. So what is parents? So parents is a map, okay. So it is a map from program locations to pairs, right. So to pairs of the form L cross um, the program the program state, right, so which is states, okay. Okay, so it is not from L, sorry. So parents is a map which is from the pairs, right. So from L cross state to L cross state, right. So when you ask something like, okay, what is parents of L comma sigma, right. So you are essentially asking, okay, I know that the program state sigma was reachable at the location L, but what was the parent state, right. So what was the parent state, right, through which this new state sigma was discovered at the location L, right, meaning that, right, let us say that if I have some L prime, okay, and I know that okay, so if I have some L prime and I know that sigma prime is reachable at the location L, right, then I am going to execute the program command which is on the edge, right, from L prime to L, and if by executing this program command I discover that sigma is reachable at the location L, then I am going to say that parents of L comma sigma is going to be equal to L prime comma sigma prime. Okay. So because sigma prime, so because sigma was discovered at the location L through the state sigma prime which was present at the location L prime. Right. So essentially this parents map, right, this is noting down, right, how a particular state was reachable at a particular location, right. So it essentially constructs this path, okay, through which a state was determined to be reachable, right. And the way this parents map is, so the parents map is also maintained, right, by this algorithm. So it initializes the parent map to not reachable, right. So this lambda x dot nr means that for every pair, right, so this lambda x meaning for every pair, we are saying that that pair is unreachable, right, because at the beginning you do not know, right, which state is reachable at which program location, right. So for every pair of location cross concrete program state, they are all unreachable. Okay. So this is the initialization. The rest of the algorithm remains the same. The only change happens here, right. So this is where the parents map is updated, right. So when you have propagated, right, from L to L prime, right, when you have propagated the state sigma to sigma prime, so you will say that parents of L prime comma sigma prime is equal to L comma sigma. Okay. So in this way, right, what will happen is, if this algorithm terminates, right, and if the error state is reachable, right, so which means that if L comma error belongs to reach, right, so you have some L error with some state, right, let us say some state sigma. So if this state is, or if this particular pair is reachable, right, then I can essentially consult the parents map, right. So the parents of this particular pair, right, this will give me the parent pair, right, from which this particular pair was discovered, right. So meaning, let us say you will get some L1 comma sigma 1, right, and then you again construct its parents map, right. So parent of this, right, sorry. So the parents map says that, so the parent of L R sigma is some L1 sigma 1, right, and similarly the parent of L1 sigma 1 is some L2 sigma 2 and so on, right, all the way. So you will go all the way up to the start location, right, which is L0 comma some sigma. Okay. So so by essentially constructing, by consulting this parents map, right, you can construct this path, right, which is nothing but an actual execution of the program, right. So this is an actual execution of the program beginning at the start location L0 and ending at the error location LR, right, which is nothing but the counter example, right. So this whole thing is the counter example. This is the actual bug that is present in the program. Okay. So this is how you can find bugs, right, using concrete model checking. Okay. Now the issue with concrete model checking, of course, right, is that so here you are maintaining the concrete set of program states at every program location, and this concrete set of program states can be infinite, right. So for example, right, if your precondition is something like x is greater than 0, right, then there are actually an infinite number of such program states, right, which satisfy this particular formula, right. So which satisfy P, right. So you will have to instantiate this P, right, with an infinite set, which means the work list will also be infinite, which means that this algorithm will not terminate, right, because you will keep on so you'll keep on removing things from work list, but since there are infinite number of elements in the work list, you will never be able to fully exhaust the work list. Okay. So the way to get around is to do what is called symbolic model checking. So as the name indicates, right, in symbolic model checking, again the idea is to compute the reachable program states, but symbolically, right, meaning using using constraint solvers, right. So using first order logic formulas. Okay. So here what we are going to do is, for each location, right, we are going to maintain a formula, right. So this reach set, right, this reach, earlier it was a set, now it is no longer going to be a set, but instead it is going to be a map from L to sigma V, right, where sigma V is the set of first order logic formulas over the program variables, right. So V is the set of program variables. So again the idea is that formula, right, whose free variables are program variables can be used to encode a set of program states, right. And now at each location L we are going to try to construct, right, or we will try to construct this formula which encodes the reachable program states at that location. Okay. So let's look at the symbolic model checking algorithm. So it also takes as input the LTS based so the program in the form of an LTS, which is sigma c, and this precondition, right, which is P, which is the start program states. But here P is going to be a formula, right. So this is going to be a formula, a first order logic formula, whose free variables are program variables. Okay. So the idea again is that you are expressing, right, the start program states, the start valuation of the variables using this formula P. So the work list here will be initialized. So the work list again is going to maintain a set of pairs, right. So the pairs here are going to be of the form L comma some formula F. Okay. So there will be pairs of locations, program locations and formulas, where again the formula has the program variables as free variables. Okay. So the work list will be initialized to this pair L0 comma P, right, meaning that again, right, all program states which are encoded by the formula P are reachable at the start location L0, right. We initialize reach of L0 with P, and for every other location we initialize reach of L with false, right, meaning that at every other location except L0 so far we have not discovered any reachable program states. So now in every iteration of this loop we remove a pair from the work list, right. So pair is going to be of this form L comma F, and then we consult the reach map, right. So if the reach map, right, so remember at the program location L, right, we look at what is the formula reach L. So if it is the case, right, that F implies reach L, right. So if F implies reach L, that means that all the program states which are encoded by F, right, or all the program states which satisfy F are also going to satisfy reach L, right, meaning that we have already discovered those program states at the program location L, right. So then we do not need to do anything, but if F does not imply reach L, right, means that not F, right, so its negation is satisfiable, right. So its negation would be F and not reach L. So if this formula is satisfiable, right, which means that there is a program state which satisfies F, right, but it does not satisfy reach L, right, meaning that so far, right, the map, the formula reach L, it does not encode the state, it does not encode all the states which are also encoded by F. So in this case, meaning that we have discovered a new state which is reachable at the location L. So then what we are going to do is we are just going to disjunct F to reach L, right. So this is this, all the program states which are encoded by F are reachable at the location L. So we update reach L by disjuncting it with F, right, and then we propagate, right. So the way we propagate is again, so we take every successor L prime of the location L, right, and then we compute this strongest post condition of F comma C, right. So if I have a successor L prime, right, which and the edge between them is labeled by the program command C. So I know that F, right, is the set of program states. So the program states which are encoded by the formula F, these are all reachable at the location L. So therefore SPF comma C, right, by definition, so this is the strongest post condition. So it will encode all the program states obtained after executing C on any program state which satisfies F, right. So this SPFC is going to be another formula which is going to encode all the states obtained after executing C on any state in F, right. So now we have discovered that SPF comma C is reachable at the location L prime. So I am going to add this L prime comma SPFC, this pair, right, of location and formula into the work list, right, and then in subsequent iterations this pair will be removed and it will be processed further, right. So it will be added into reach and further propagated into its successors and so on. So at the end, when this while loop terminates, meaning that you have exhausted all possible executions of the program, right. So you have found out all the reachable states at every program location. We again ask whether or not is the error state reachable, right. So is reach L equal to false or not, right. So if reach L error rather, so if this formula is not equal to false, that means that some concrete program state is reachable at that location, right. So which means that the program actually has a bug. Okay, so this is symbolic model checking. Now again, right, I have not shown how to augment this with counterexample generation, but you can do that as well, right? So you can add the parents map similar to how we added it in concrete model checking, and keep track, right, of how a particular program state was reachable at a particular program location. Okay. So what is bounded model checking? So bounded model checking is the same as concrete or symbolic model checking. So you can instantiate bounded model checking with either, right, but for a finite number of steps. So essentially, right, I mean, in either concrete or symbolic model checking, I have this while loop, right, which in principle, right, can run infinitely, right, or can run at least for an unbounded number of steps, right. So in bounded model checking, I put an artificial bound on this loop. So I will say, okay, I am not going to run this while loop for more than some n number of steps. So that's what's called bounded model checking. So which is to do concrete or symbolic model checking, but for a finite number of steps. Okay. So there are multiple ways to do this bounded model checking. Right? So one way is that, so one way which, or rather one reason, right, why the while loop, right, in model checking, the model checking algorithm can run for an arbitrary number of steps is because of loops in the program. So if you have loops in the program, then you will keep on discovering new program states, right, in the program locations which are inside the loop, and then that while loop is never going to terminate, right, irrespective of whether you are using concrete model checking or symbolic model checking. So what you can do is we can unroll the loops in the program for a fixed number of iterations. Right. So unrolling loops in the program meaning that you remove the loop, right, and instead you replace the loop with copies of the body of the loop, right. So how many copies? Well, that is decided by the bound, right. So you can a priori decide, right, how many copies of the loop body I am going to make, right, but this is going to be for a fixed number of so there will be a fixed number of copies, right. So once you do that, right, now the program is no longer going to have a loop. So you simply do concrete or symbolic model checking using the same algorithms that we have seen in the previous slides, right, on the resultant program. Okay. So now in particular concrete model checking may still not terminate, right, because you are doing things concretely, but symbolic model checking, right, this is guaranteed to terminate, right, because you will be able to express, right, the set of reachable program states using using formulas. Um, so in this way, by unrolling loops for programs with loops, you get bounded model checking. This is one way to do bounded model checking. Another way, right, is to apply what we call a static single assignment transformation, right. So this is again something that we saw way back, right, when we looked at this Microsoft Zune example, right. So where we had a program, right, with loops which we unrolled, right, and then once you unroll the program, right, instead of running the concrete or the symbolic model checking algorithm that we saw on the previous slides, what you can do is you can directly encode that program in first order logic, right. So this is what we did in the Microsoft Zune example, right, where we actually did bounded model checking, but without running this concrete or rather without running this model checking algorithm. So we did not run the model checking algorithm, but instead we directly encoded the model checking problem in first order logic, right. So this is also another way of doing bounded model checking, right. But the main idea is essentially to do concrete or symbolic model checking for a fixed number of steps, right, or a finite number of steps.